All right, today we're going to tackle a question that's, well, it's pretty fundamental to chemistry, to environmental science, even to medicine. It's a challenge that pops up every single day in labs all over the world. Now, seriously, think about it for a second. How do you know the exact acidity of your coffee? Or, say, the amount of fluoride in your drinking water? Or maybe the concentration of some pollutant in a lake? You can't actually see the individual ions floating around in there. So, how on earth do you count them? Well, it turns out there's an incredibly elegant answer, a technique called potentiometry. And the core idea, it's pure genius, really. You can figure out the concentration of something you can't see just by measuring a tiny electrical voltage in the solution. Okay, let's dive into this because it's such a brilliant concept. The entire technique hinges on this one single principle. You see, when you place a special pair of probes, we call them electrodes, into a solution, they generate a voltage. And here's the magic part. The size of that voltage is directly tied to the concentration of a specific ion. It's a measurable signal for something that's totally invisible. Now, this isn't just some happy coincidence. It's all governed by a famous piece of science called the Nernst equation. Look, we're not going to get bogged down in the math here, but the crucial takeaway is that this equation is the rule book. It gives us the exact, predictable link between the voltage you can measure on a meter and the concentration you're actually trying to find. So how do we actually do this? Well, you need a two-part toolkit. First up, you have the reference electrode. I want you to think of this as your unchanging yardstick. Its whole job is to provide a perfectly stable, constant voltage, no matter what. Then you have the indicator electrode. Now this one is the sensitive probe. Its voltage changes depending on how much of your target ion is in the solution. And the difference in voltage between that steady yardstick and the changing probe, that's your answer. To really get a handle on this yardstick idea, we've got to start with the ultimate standard. This right here is the standard hydrogen electrode, or SHE for short. Now what's so cool about this thing is that it is the universal 0 point. By international agreement, its potential is defined as exactly 0 volts. Every other electrode in the world of chemistry is measured against this one. So, while the SHE is the official gold standard, in a real-world lab, you're much more likely to see something like this, the Calamo electrode. Our source material points it out as one of the most common reference electrodes out there because, it's easy to make and, most importantly, it gives you that rock-solid, constant potential we need for our yardstick. And check this out, this table just nails the point home. It shows the super precise, reliable potentials for these common reference electrodes. See that? The saturated Calamo electrode, at room temp, it's always going to give you plus 0.2444 volts every single time. It's a known constant value. And that's what makes it such a trustworthy anchor for all our measurements. Okay, so we've got our stable yardstick. Let's move on to the other half of our toolkit, the sensitive probe. And this might just be the most famous indicator electrode of all time, the glass electrode. This thing is an absolute marvel of engineering, specifically designed to be incredibly sensitive to the concentration of hydrogen ions, which is just the scientific way of measuring acidity, or pH. So how in the world does this thing work? It's pretty fascinating. You dip that little thin glass bulb into your solution, right? And a tiny electrical potential forms on its outer surface. And here's the key. The size of that potential changes in direct response to the solution's acidity. That changing external voltage is then measured against a super steady, constant voltage inside the electrode itself, and that gives us our precise reading. All right, we've got our stable reference electrode and our sensitive indicator electrode. It is time to put them together in one of the most powerful applications of this science, a technique called potentiometric titration. This is pretty much what it looks like in the lab. You've got both electrodes placed right in your sample solution. Then from that long glass tube up top, that's called a burette, we add a second chemical, really slowly, literally drop by drop. And the whole time, a meter is constantly reading the voltage between our two electrodes. So what are we looking for? What's the whole point of this? The source material puts it perfectly. We're watching that voltage, just waiting for the exact moment a chemical reaction finishes. And that moment, the end point of the reaction will be revealed by a sudden change in potential. And as we add that second chemical, we're plotting that voltage reading on a graph. In the beginning, as you can see, the potential does change, but it's really slow and gradual. We're just kind of creeping along, adding more liquid, and the voltage is barely nudging upwards. We just keep adding drop by drop until, suddenly, boom, the potential makes this massive, dramatic leap. This is it. This is the sudden change we were waiting for. This super steep, almost vertical part of the curve is called the inflection point, and it signals with absolute certainty that the reaction is complete. Now, trying to eyeball the exact center of that steep line can be kind of tricky, but here's where a little bit of math makes everything beautiful. If you plot the rate of change of that voltage, what's called its first derivative, that S-curve transforms into something incredibly clear. You get an unmistakable, sharp peak. The very top of that peak is the endpoint. No question about it. So the crucial takeaway here is that this peak takes all the guesswork out of the equation. It allows us to pinpoint the exact moment the reaction finished with just incredible precision. There's no ambiguity, just a clear, sharp signal. So let's do a quick recap of what we've learned. First, potentiometry lets us measure the invisible by linking voltage to concentration. Second, it uses that two-part toolkit, a stable reference yardstick and a sensitive indicator probe. Third, when we do a titration, we watch for that sudden, dramatic jump in voltage. And finally, we can transform that jump into a super sharp peak to find the reaction's endpoint with amazing precision. And this really brings us to a final, powerful idea. Our sources explain that we can build these sensitive electrodes to detect all sorts of different ions. Sodium, potassium, fluoride, you name it. The technology is incredibly versatile. Which leaves us with this question. If we can design a special probe to measure almost any invisible substance we want, what other mysteries are out there just waiting to be measured?